Okay, guys, in this video, we are going to actually get into the testing and computing confidence interval for matched pairs data. So the first example here that we're going to look at is the weight loss program and whether it worked or not. So we already discussed that we have two samples, but they are paired or matched. So you have individuals' weight before and after. So this is before the individual entered the weight loss program and then after. And so this is like number one, this is number two. And we already talked about the fact that if a weight loss program worked, that means the weight before should be larger than the weight after, right? Because the individual lost weight. Okay, so this should be smaller. And that means that this is going to be a right tail test because you always go from smaller and open it towards the larger one. All right, so let's take a look at how to actually conduct the test. Now here we have the data, and as before, this is observations on the same individual. So frequently they will be asking you, why is this dependent on matched pairs? You're going to say, well, this is the same individual's observations. So obviously the same individual's observations depend on each other. Okay, so let's get into Desmos. So what I did is just, I entered two lists. Now you can call them whatever you want. I call them X1 and X2. You can call them B for before and A for after, however you want to do that. But if you're wondering, like, how did I type X1? I literally just typed capital X and then number one. And Desmos automatically switches this to a subscript, okay? The first thing you do when you do matched pairs is you're going to construct the differences. So you're going to create a new list L that's going to be equal to x1 subtract x2. So this you have to write down on your card because nobody's going to tell you that. The differences are always going to be x1 minus x2 if your first data set is in number one and then in number two. And so frequently you will have a, blanks to fill out for the differences. So, for example, the first person lost 22 pounds, the next person lost 21 pounds, and so on. The difference between before and after, okay? Now, what else can I ask you about the differences? I can ask you to compute the mean of the differences, and you should know how to do that because you already know that the mean is mean of L, right? If you are saving L, if L is your differences. If, for example, I say, okay, now compute standard deviation of the differences, you should also be able to just compute STDEV of L. If you want sample size of the differences, this should be 6. I mean, you can see it, but if you want to, there's a command count that will compute them for you. So there are 6 observations. Okay, anyway, so all of that right now we do not need. We only need L. Really, once you computed the difference between the two samples, you can disregard them. They're not needed anymore, okay? Don't delete them because then L is not going to be defined, but you don't want to look at them. You only want to look at the differences. Okay, so let's go ahead and do the testing. So we're going to click on the plus sign. We're going to go to inference, and you probably already guessed that because this is the test for the mean, we're going to go to the t-test. But this is going to be a big difference with what we had when you had two independent samples. Here you were saying, okay, the list is in X1 and the second one is X2. That was when it was independent. That's no longer the case. Here for the differences, you are going to only have one sample and the sample is going to be of the differences. So please write this down somewhere that, again, when you are doing a test for matched pairs or differences, you are only using one sample and that is the differences, okay? And then we're going to click on create test. Now, here, depending on what we want, if we want the test, then we're going to use significance test. If we want confidence interval, in a second we're going to look at that, but let's say we want to do the test. Do not ever change the null hypothesis. This should just be mean difference is 0, okay? But what you need to know is, what do we put for the tails? Is it going to be left, both, or right? Remember, we decided that it was going to be a right tail test. And in a second, we should be able to verify that by looking at the test statistic. So this should be right. So if it's right, then the test statistic should be positive. Most of the time, it should be positive. Okay, so let's look at it. Do you see the test statistic right here? And it is definitely positive. So that's another indication that what I selected here is right. Because a lot of times people say, oh, it says lost weight, so it has to be less. No, it didn't. Okay, if you lose weight, your weight goes down. So, and then another thing that could have happened if you decided, for example, by mistake, that it was left, you will see a p-value of 1. So any of you, like, I don't care, you maybe you are the genius, whatever, if you ever leave the p-value equal 1 or 0.99999 or 0.99998 or something like that, I will not give you partial credit. Forget it. Okay, I don't know you, I don't know what your name is. Okay, I hope I made myself clear that p-value of 1 is not going to happen. P-value, what does this mean? Well, that means it's just very small, which means it's highly significant, which should be happening because your differences are very big. Like, these people lost a lot of weight here. So it definitely makes sense that p-value is basically 0. Okay, so if you want more decimal places, you can, of course, look under the 3 dots and you can see your t-score or test statistic. It is huge, it's 16 point something. Overwhelming difference against the null hypothesis, so we're gonna definitely reject it, and I will say the weight loss program worked. Okay, now what else we're gonna do is the confidence interval. Okay, so what about confidence interval? So if we need to do that, let me show you before we get to the assumptions. It's going to be identically the same thing as we had for the independent case in terms of the interpretation. So remember, I told you that you need to have this stuff on your card. And let me see if I can get to it. Like, where is the where are the cases? There are the cases right there. Okay, so this is your, if you remember, if you don't have this stuff, man, oh man, you need to know it. So it's going to be exactly the same interpretation. You just need to know what is number 1 and what is number 2. So let's go ahead and let's say, for example, compute a 95% confidence interval here. So we expand the confidence interval menu. We leave this at 0.95. And this is the 18.2 to 24.8. Again, if you need more decimal places, you are more than welcome to look here. These are your lower and upper bounds for your interval. Now, how are you going to interpret it depends on the case. Case number 1, minus plus, no statistically significant difference between the means. That did not happen here. Here we've got plus, plus. Both of these numbers are positive, which means that we have case 2. Case 2 means that the population mean number 1 is larger than 2 by whatever other bounds. So I'm going to say I am 95% confident that the mean before I started the weight loss program, my mean weight on average was by 18.2 to 24.8 pounds higher than after I finished the program. So this would be a very important thing to know, right? If you lost weight and by how much, right? Not just is it significant, but by how much. If you are given 18 to 24.8 pounds, I sign up for that, sign me up for that stuff. Okay, so the last thing we're gonna do is check assumptions here. So how do we do that? Okay, so this is gonna be a little bit tricky. Hold on. Okay, so how do we check assumptions? So we are gonna have to do this using normal probability plot. But maybe you can guess whether the list here will be x1, which was the first sample, x2, which was the second sample, or the differences. Can you guess? I'm going to pause and see if you can figure it out. It's going to be the differences. Okay, so what we're going to do is make 2 lines here in this worksheet. And we are going to copy both of these that we just used in here, in the normal probability plot worksheet. So copy that, and then delete what it says under L and just put x1 minus x2. So you want the same thing that was over here. You want to copy this over here, and you need to call the list L. Otherwise, this worksheet does not understand what the heck is going on. So this is your correlation. And then you're going to compare that correlation, which is correlation of the differences, not of each sample separately. You're going to compare that with the critical values table. Now, in terms of the sample size, sometimes people get confused because you have 2 samples. One has 6 observations, another has 6 observations. So does it mean that the sample size is 12? No, it doesn't. Because again, everything here is about the differences. This plot these are the differences. This is not each individual sample. So you are looking up the value under 6. However many differences you have, that's your sample size here. And that's 0.889. So here I say 0.9485 is definitely larger than 0.889, which means that assumptions are satisfied. We were able to test successfully.